Welcome to the video presentation session. Analog electronics. How can we define and understand analog electronics? Analog electronics are definitely the system with a continuous variable signals. Unlike the digital signals, which will be having only the two levels, either the low or high, these analog signals are continuously variable output signals in response to a voltage or current that represent a signal. And to begin with this analog electronics, we have to know the basic building block of any substance in this universe. Definitely the atom. Atom is basically the tiniest particle of any substance, and it consists of the central nucleus having positively charged protons and with no charges neutrons, and there are equal number of electrons to that of the protons present in the nucleus, which will be revolving around the nucleus at different radial distances. Number of electrons in any orbit is calculated using the empirical formula 2n square. All these things are very basic things which you might have studied well in your higher schools. Coming to the conductors. You may all know about these conductors and insulators. Conductors in the sense electrical conductors. These are the materials which allow the current to pass through them. And the example for these conductors are almost all the metals like silver, gold, copper, aluminium, iron, and even there are gaseous conductors and liquid conductors. And these examples for gaseous conductors and liquid conductors are kept as your assignment part. You have to search the examples for gaseous form of conductors and liquid form of conductors. And basically these are the materials which will be conducting the electric current through them. And in these materials, conduction band is filled with a large number of free electrons. Then what is this conduction band? Actually, all the energies of the electrons present in any substance is represented by a two-dimensional diagram called as energy level diagram. As you can see in this picture here by the side of the description, wherein you can find only the valence band and conduction band. Below this valence band, there will be the lower level of energy bands. Means the first orbit electrons will be having the smaller amount of energy and are tightly bonded with the nucleus. That will be represented by a simple band, and next to that will be the second orbit electron energy, which will be having little bit higher energy than those of the first orbit electrons and are quite loosely bonded with the central nucleus than that of the first orbit electrons. And the same pattern will continue, and the last orbit electrons are called as valence electrons, and the energy of these electrons is represented by a band which is called as the valence band. Above the energy level of this valence band lies the conduction band, wherein the electrons will be free from atom and will be very much free to conduct the electric current. and the electrons which are present in this conduction band will be contributing much to the conduction of electric current. And in this diagram you can see that valence electron band and the conduction electron band level are overlapped with each other in case of these conductors. That's why we can find more number of free electrons in the conduction band, and the electric current can easily be conducted through these conductors. And that's why we say that the band is completely filled with free electrons in case of the conductors. Coming to the energy level diagram of insulators. However, there is a large energy gap between the valence band of energy of electrons and the conduction band of energy. And this would be of the order of around 15 electron volts, and which is very much huge, that one electron from the valence band of energy can acquire and jump into this conduction band is almost an impossible task. That's why in these insulators, conduction band is almost vacant. It is not at all containing any free electrons. Where there is a vacant conduction band with no free electrons, that such a substance will not at all be participating in conducting the electric current through it. That's why it's called as an insulator, which do not allow the electric current to pass through them. Next comes the energy level diagram of an interesting substance called semiconductor. Semi means it is in between that of the conductor and insulator. And that's why the energy gap between the valence band and the conduction band in case of these semiconductors is about 1.1 to 1.5 electron volts. This would be the smaller energy gap called as the forbidden energy gap, which an electron present in the valence band can easily occupy by the room temperature or the voltage that we externally supply. And gaining that extra energy, the electron will jump from this valence band into the conduction band to become a free electron. Once a free electron is generated in the conduction band, means transferred into the conduction band, it leaves behind a hole in the valence band. And this process is called as electron hole pair generation. This can be generated, or this process can be happening in many ways. Later in our sessions, we will be even coming across how to generate an electron hole pair. So once the conduction band is having a few number of free electrons with the excited atoms by the room temperature or the external voltage, they contribute in conducting the little current. That's why these semiconductors under the absolute 0 degree centigrades will be having no electrons in the conduction band and behave like a perfect insulator. And when brought into the room temperature, a few free electrons are available for the conduction of current in the conduction band, and they start conducting electric current gradually. That's why these are called as semiconductors, having the electrical conducting property in between those of the conductors and insulators. As the material can be configured between these conductors and insulators, that's why we call it as a semiconductor. And The best example for this pure semiconductor is germanium with atomic number 32 and silicon with atomic number 14. Then coming into the significance of these semiconductors. Significance of these semiconductors in the sense, why do we need to study the properties and the subject on these semiconductors? Why it is so important? Yes, it is very much important to study the semiconductors because the controlled conducting property of the semiconductor has marked advantage and it is used to devise many electronic components. Many electronic components in the sense the components which will be conducting only in one direction and not in the reverse direction, and the device which we called as a diode. And a diode you may be knowing already. It's a two-terminal one junction device which will be characterized to conduct the current in only one direction but not in the reverse direction. Similarly, another property, another device of this semiconductor is that the transistor, which will be having the current to be transferred from a different resistance path of the input through the output, having many advantageous features. Initially, these transistors were in the discharge tubes of the size of many foots. Nowadays, the size of these transistors with the invention of these semiconductor devices has brought down to the size of our even the fingertip and less than that fingertip. Later in our sessions, we will come across all these devices. Even the MOSFET is a variety of those transistors which is still advanced than these transistors. Coming into the field of these solar cells, which will be converting the light energy into the electrical energy. The material which is involved in converting this light energy into the electrical energy is definitely the semiconductor, solar cell that we call it as. The street lamps and the lamps that we use in our home. Initially, it was an incandescent lamp in our home, even the fluorescent tube in our home initially. Now all these lamps are replaced by the LED lamps that every one of you may be aware. And this LED is a beautiful product outcome of this semiconductor only. And similarly, we are having many electronic gadgets, our mobile phones, our any remote signals, and even the smart devices, the computers, the power electronic devices, the satellite equipments, communication systems, even the defense system equipments. And all these will be utilizing the electronic devices which are devised out from these semiconductors. That is why the study of the semiconductor is much important here. Coming to the crystalline structure of this semiconductor. As I mentioned earlier, just a minute back, that a very good example for this pure semiconductor is silicon with atomic number 14 and the germanium with atomic number 32. The atomic structure of this silicon is seen there, wherein it is having 14 protons and 14 electrons distributed around this nucleus, as you can see in the circular sketch. And in the outermost shell, you can see that there are 4 electrons, which are called as valence electrons and is called as a tetravalent substance. When the silicon is available in the crystalline form, each silicon atom will be sharing one electron with its surrounded neighboring electrons of the atom, as you can see in the sketch there. And to make this diagram very much simple, even you can draw the diagram, just you can view it on the screen. So this one, wherein you can represent the central silicon core of the atom surrounded by 4 valence electrons. All these valence electrons will be shared between the neighboring atoms' valence electrons surrounding each atom. And this is the crystalline structure of any semiconductor here. Similar will be the crystalline structure of the germanium. You can try yourselves while you practice this subject. Then coming to the doping. What do you mean by this doping? Before to go to this doping, these semiconductors, when put into the room temperature, the outermost orbit electrons will be acquiring extra energy and they will be leaving the parent atom and becoming a free electron. They will jump into the conduction band. When they jump into the conduction band, they leave behind a hole in the covalent bond formations. So this electron hole pairs will be constituting the reason for conducting small current in a pure semiconductor, which is purely dependent on the atmospheric temperatures. To make this electrical conductivity higher, irrespective of the room temperatures, the process called as doping is adopted. So doping is the process of adding a small quantity of impurity atoms, either a trivalent or pentavalent impurity, to a pure tetravalent semiconductor substance. With this, the conducting property of the resultant material will be marginally increased. Then, depending on this doping agents or the impurity that we add into the pure semiconductor, there are types in the semiconductor. Coming into the basic category of this semiconductor, we can classify the semiconductors as the intrinsic semiconductors. Intrinsic semiconductors are nothing but the pure form of semiconductors. Example, germanium with atomic number 32 and silicon with atomic number 14. So the next variety of these semiconductors are extrinsic semiconductors. When an impurity atom, either a trivalent or a pentavalent substance, is added into a pure tetravalent semiconductor, the resulting semiconductor is called as an impure semiconductor or a doped semiconductor, or is also called as an extrinsic semiconductor. Depending on these dopants, these doped semiconductors can be either a p-type or n-type semiconductors. Now, how this p-type semiconductor is resulting? When an impurity having 3 valence electrons like boron is added, only 3 neighboring silicon atoms are bonded. 1 electron will be missing from the covalent bond. This missing electron in the bond is referred as a hole. Hole is assumed to be having a positive charge. Why it is assumed to be having a positive charge? Later you will be knowing, because as it is finding a scarcity of 1 electron in fulfilling the maximum 8 electrons in the outermost shell to create a crystalline structure there, it will be eager to accept one electron. When an electron can be accepted or dragged or attracted, then definitely it will be attracted towards a positive charge only. That is why if a hole is capable of attracting an electron from the neighboring atom, then it is assumed to have a positive charge. Then, as these holes will be trapping electrons from the neighboring atoms, they become the reason for the movement of the electrons through these substances. And this movement of electrons through these holes constitute the movement of valence electrons, creating the small current. And this current is also called as current due to holes or current due to valence electrons. Then the other type of the semiconductor, extrinsic semiconductor, is the N type of semiconductor. This is the result of doping a pentavalent impurity substance like antimony into a pure tetravalent semiconductor, as each impurity atom is surrounded by 4 neighboring silicon atoms here. It will be sharing 1 electron with each surrounding neighboring 4 silicon atoms, and 1 electron will be freed from this antimony atom. And this free electron, which is not at all participated in any bonding sequences or any bonding process, will be free to move, and this is called as a free electron. As this pentavalent substance can donate 1 free electron to conduct the electricity, the substance, impurity substance, is called as a donor impurity. A donor impurity is called so because it can give out 1 electron as a free electron. That's why pentavalent impurities are also called as the donor impurity. On the contrary, when a trivalent impurity is added, as you can see in this case of a p-type of semiconductor, a hole is generated and this hole can accept 1 electron. That is why this impurity, which creates a reason to accept 1 free electron, is called as an acceptor impurity. That's why the trivalent impurities are called as acceptor impurities and pentavalent impurities are called as donor impurities. In any of these extrinsic semiconductors, total number of electrons and positive charges present in the resultant substance are equal. That is why electrically either a p-type substance or the n-type substance is always neutral. Then coming to the resistance of these semiconductors. If the doping atoms are more in number, they generate more charge carriers. Charge carriers in the sense, in case of a p-type of semiconductors, holes are the charge carriers, as they can transfer or electrons can move through these holes. A hole is always called as a charge carrier. And in case of n-type of semiconductor, it's a free electron which is moving, and a free electron is called as the charge carrier. Depending on the percentage of doping, concentration of these doping means addition of the quantity of impurity substance, more number of holes or more number of free electrons can be generated. If there are more number of charge carriers are present in the in the resultant substance, then much current can be transferred through the substance, and the resistance of the substance is said to be less. And this is how one can have the controlled doping to get the required resistance for the resultant semiconductors. As I just scripted you or illustrated you what these donor and acceptor impurities, the same is available in the script form. Later on you can pause the video, note down all these things that I have told you and I have scripted you in your own writings in the notes, and present it whenever we are asking you to present. Okay, so wish you happy learning.